Jump into the next section a little bit because the next thing we have after tomorrow's quiz is the gateway on antiderivatives. I think we've set the stage here to show with, well, both parts of the fundamental theorem that antiderivatives play a role here in this idea of area of an integral. Now, our goal then going forward is to talk about why is that important. We've talked a little bit, distance. If you take a velocity curve, look at the area underneath, that's the distance traveled. We did average value of a function. The average value of a function involved the area. So we just had a couple of examples where an integral could be involved in finding something interesting. So that's enough, I think, to just say, all right, let's investigate this a little more. And so if this right here means that the area function itself as a function, kind of like the slope function, was a plotting of all the different slopes of a function. This is the plotting of the different areas under a little f graph. And we found out that that function that was created, that area function, is the antiderivative of the little f that the areas are under. Okay, so that gives us a reason that, hey, okay, antiderivatives are kind of important. And then, of course, that led us to this, Fundamental Theorem Part 2, which is a way to find a piece of area under any kind of function if we can find the antiderivative. As we'll come to learn, there are some functions, pretty simple ones. This function right here, there is no antiderivative of that. And when I say no antiderivative, I mean no closed form equation antiderivative of that. Okay, there's clearly, though, an area. If you graph that and look from 0 to 2, there would be an area. We just would not be able to find the area using this, because this means you have to be able to do an antiderivative of that function, and there is no equation that when you do the derivative of it gives you this. There's just no equation that when you do the derivative of it will give you sine of x squared. And so therefore, there's no antiderivative of sine of x squared. Okay, and so then this is not going to work. So we are going to have to investigate some other ways of calculating areas that we'll get into more in chapter 6. Okay, but for right now, we're going to focus on this one, finding antiderivatives, and so that's why the gateway test will be important. So for tomorrow's quiz, just some simple antiderivatives, just power rules, maybe sine and cosine going backwards, that kind of thing. So we're going to work on that a little more in our homework 19 through 30 there on that one. Or was that the section? No. Yeah, 19 through 30. So talk about some of those and see if you guys had some questions on those antiderivatives. So just kind of some basic ones. We'll get into some tougher ones a little bit today, but that's not going to be on the quiz tomorrow. But we want to go ahead and start talking about it anyway. Okay, I don't think it should screw us up for the quiz tomorrow. I hope not. Okay. All right. So that's just kind of a little bit of summary of that. So the two parts of the fundamental theorem, this one just tells us that the area function is the antiderivative. So we looked at that free response question yesterday if we see an area function, we just know it's an antiderivative. And this is how we can use the antiderivative to find a definite integral, a fixed piece of area. Okay, so I want to talk about that in just a minute. So backing up to the beginning of the chapter 5 was where we did a definite integral. So tomorrow, if you remember what we did, let me jump ahead. I'll have this back up here if you want to copy this down. But when we started in section 5.1, it was finding areas geometrically. So we had a picture like this, and we could just find areas. Do the integral from 2 to 6. And then we would just we would have geometric areas, okay? And then we had those formulas for splitting up the integrals, okay? So we started this chapter in trying to find, with this idea of a definite integral, a fixed piece of area, a constant. Now, what I've written down here is these are the ways that we have and will have of finding that piece of area. If we have a function, okay, and we want to do the area under it, we have 3 ways we can do that. One is just geometry, and that's the first thing we did at the beginning of this section. So you'll probably have some of that tomorrow. Okay, so triangles, trapezoids, half circles, whatever. Okay, so be able to do that. The second one we're not really getting into. Now, we've done that. We talked about it at the very beginning of the year, just counting squares. Counting squares and just kind of approximate what the area is. Now, we're going to refine that in Chapter 6. We're going to get a lot more into approximation because, quite honestly, that one comes into play when we can't do the third one. Okay, so the third one's the one we learned yesterday, the fundamental theorem. That's going to be the one we go to first. Well, geometry, I guess, is easy enough, but that doesn't happen very often. You got to have lines and have circles, and that doesn't happen a lot with most functions. So usually we go to this. Do the antiderivative, work it out. If there is no antiderivative, then we don't have no choice. If we can't do geometry, then we got to do approximation. So we're going to get into that more. Okay, but that's where machines come in. If you type into your calculator, well, let's do it right now. Get your calculator out, which, by the way, it's no calculator tomorrow, because you're not going to have to do anything like this tomorrow. But that function I had up there a minute ago, sine of x squared, do the integral of sine of x squared from 0 to 2. Do the integral of sine of x squared from 0 to 2. Okay, and what do you get? Get a decimal, right? Sine of x squared from 0 to 2, you get a decimal. Because there is no antiderivative, so the calculator is going to try to do an antiderivative, and if it can't, it's going to do an approximation technique. We're going to talk a lot more in Chapter 6 about how it's doing that, and that's why it gives you a decimal right away. Now, change it to sine of x. Do sine of x from 0 to 2. Okay? Do sine of x from 0 to 2. What do you get? Take out the x squared. 1 minus cosine 2. See how it gave you an exact answer? That's because it did the antiderivative of sine, right? Which, by the way, what's the antiderivative of sine? Antiderivative of sine. Negative cosine, right? How do you check? Do the derivative, right? Do the derivative. So that's something you have to do tomorrow, right? If you have to do a fundamental theorem part 2, it's like this problem right here. You do the antiderivative sine, it's negative cosine, and then you plug in a 2, plug in a 0. So you get negative cosine 2 minus negative cosine 0. What's cosine 0? 1 minus a negative is plus, so negative cosine 2 plus 1. Now the calculator wrote it 1 minus cosine 2, but you guys can get the same thing. So the calculator will try to do it with an antiderivative like it did on that one. If it can't, it will do an approximation, which is what it did on that other one. Okay? And so those are the 3 ways we will have to find a fixed piece of area. Okay? Now we're focused right now on 1 and 3 here. Right? You probably have to do a little geometry tomorrow, and then you'll have somewhere like 19 through 30 today. You do this. Okay? This one will come later. Number 2. Okay. So let's do this. This is kind of looking ahead here a little bit, but this kind of organizes our thinking a little bit too. I mean, this isn't really looking ahead. This is more for the quiz. Okay, I got 3 different integrals on this page. Okay, now they're closely related. Okay, these have t's in them. Why do they have t's in them? Because you're using an x up here. This one has x's. Because there's no problem. This is a definite interval. Now, I could have put t's here, right? Could have put t's here, but if I didn't need to, I could put t's or z's or u's or w's or whatever in here, right? It's a parabola. This is the area under a parabola from 3 to 4. Okay, so how would we work this out? Okay, let's do it. Okay, so we would do what? Let's do fundamental theorem part 2. So what do we need? What do we need? Antiderivative. So that'd be 1/3 x cubed, right bracket, 3 to 4, right? And then we plug in a 4. So 4 cubed is 64. So 64 thirds. Then plug in a 3. 27 thirds. And that would equal, what, 37 thirds, right? But the important thing is this is a constant, a number, a fixed piece of area. right? This is a definite, this is called a definite integral right here, okay? So understand the different types of integrals that we may see. So this is a definite integral. It's a constant, a number, a fixed piece of area. This particular one happens to be 37/3. Okay, and we can work it out using fundamental theorem part 2. So that's something you're going to have to be able to do tomorrow, right? And you're going to have to be able to understand that concept, that that's what that is. Okay, now let's go to the next one. What is that? That is not a constant. That is not a number. That is not a fixed piece of area. What is it? What do we call that? I just said it earlier. What is it? What is this right here? It's the antiderivative, but before we learned it was the antiderivative, what do we call it? Area function. Area function. This is a function, right? And some of you may have said it, but not very loud. We're real confident. I get you reading my mind there a little bit, but it's a function. That's different than a number, a constant. It's a function. It's a bunch of different areas, right? It's a bunch of, this is the areas under the parabola from 3 to 4, from 3 to 5, from 3 to 6, from 3 to 7, from 3 to 0, from 3 to -8, right? It's a whole bunch of areas. This is an area function, okay? Now, can we find the formula for this area function? Sure. It's what? 1/3. How'd we do it yesterday? Isn't this the one with the free initial condition, right? So isn't this 1/3 x cubed plus c? And then how do we get the c? Give this a name, call it g. So g of 3 would equal 0. But in other words, plug in a 3, right? You don't have to call it g. You can just say, well, this is the one where we plug in a 3, and we're going to get 0, right? So what 3 cubed is 27, divided by 3 is 9. 9 plus c equals 0, so c equals -9. So what is this? This is 1/3 x cubed minus 9. So this is a specific antiderivative is what it is. It's an area function, but it's a specific, a unique antiderivative of this function in here. Okay? So that's very different. So understand the difference here. Now, because we did learn fundamental theorem part 2, now we don't do this very often, but you can do this. Instead of thinking of it as a free initial condition, you can actually apply fundamental theorem part 2 here. Let me do it in the red. You can actually do this right bracket with this. You could say, oh, you know what? The antiderivative of that is 1/3 t cubed. I always find that some people like this a little better once we've learned the right bracket notation. You could say this is 1/3 t cubed from 3 to x. And now what do? You plug in an x, so you get 1/3 x cubed, and then minus, and now plug in a 3. You get 1/3 3 cubed. And what is that? That's 1/3 x cubed minus 9. See how that's the same thing? And some people, that makes sense sometimes, because we're already doing the fundamental theorem part 2 on this anyway. But I really like the blue too, because I really want you to understand where that came from, because that's how we learned it first, that this represents a function, this represents an area function with some plus c, and then knowing 3 is like knowing a free initial condition, that when you plug in a 3 you get 0, and you come up with the same thing. See how that works? So I don't care how you do that. So if I give you one like this tomorrow, and say, find a formula for this. You want to do it the way I did it in the red, or you want to do it the way we did it in the blue with the free initial condition, I don't care. They're both the same thing. Both the same thing. Okay, so then what's the difference in number 3 then? What's the difference there? We don't know the left endpoint. We don't get our free initial condition. Well, if you don't get your free initial condition, then what's that mean? You don't know what? You don't know C. You can't find C. And so what this is, this then, let's go back to the blue. This is just the general antiderivative. This is just the general antiderivative where we don't know, we're not given a specific initial condition. So this is just 1/3 x cubed plus c. This is just 1/3 x cubed plus c, because we not only don't know the right endpoint because it's sliding and varying and changing, but we don't even know the left endpoint either. And so we don't know, I mean, it's just the general antiderivative right here. Now, what we're going to do going forward is we're going to, if we get a situation like this, where if we don't have a left endpoint, we don't have a right endpoint, then the question is going to be, why even write these two things on here? If this is just going to represent the general antiderivative, what we're going to do, and let me write it in black here, what we're going to do is we're going to take this thing, and we're just going to say, well, let's just do this. Let's just take off both of those things. What good are they doing? They're not really helping us do anything. And then when we take those off, we don't even need to play around with this t anymore because we take that off there. And so what we're going to do is just this. And so this is called an indefinite integral. Indefinite, right? It is not a fixed piece of area. And so this is going to be called an indefinite integral. All it means is find the general antiderivative. Find the antiderivative. So it's kind of, that's what your gateway test is going to look like. A big chunk of your gateway test is going to be those problems right there. And all that is saying is do the antiderivative. That's called an indefinite integral. And it's just going to give us this. Okay? So it's going to be 1/3 x cubed plus c. Do the antiderivative is what that's basically saying. Okay? All right. So that, and I like that because that shows us where this comes from. So when you look at your homework for tomorrow. Matter of fact, well, on 19 through 30, those are all definite integrals. So on the gateway test, you might have a couple that are definite integrals where we actually have to work them out and get the number answer. But most of the gateway test is just going to be this. Find the end. Now, I could ask it this way. I could give you little f and then in the direction say find big F. Be the same thing. Okay? But that's the notation we use that says find the antiderivative. Okay? But you can see where it comes from, where that notation comes from. All right? Okay, so quiz tomorrow is going to be mostly this, right? Mostly this stuff right here. Something about an area function, maybe with your free initial condition. We've been working on that. And, of course, we've been working on this a little bit, too. Okay? All right. So, homework questions. Homework questions. Okay. Okay, so 65 is, so they give you big F and big G, which are two different area functions, right? They're both a to x. Okay, so they're two different antiderivatives, right, of little f and little g. And so big G is the antiderivative of little g, and big F is the antiderivative of little f. And it says that little f is littler than little g. Okay? So the key to this one is to put this in terms of speed limit law. That's basically what this problem is. Okay? So let's put it in terms of derivatives. So if you have big F and big G, then what would you call little f and little g in terms of derivatives? Wouldn't that be big F prime and big G prime? Those would be the slopes, right? So what you're saying there is that, and they're both starting at A. In other words, for both of them, big F of A is 0 and big G of A is 0, right? In other words, they have the same left endpoint, right? So what you have here, so I want to first do it as slope. So that would tell you they're starting at the same place. So they're starting together, and little f is less than little g. Well, that means that that's their rates, their slopes, their speeds. So that means little f is going what? Slow. So therefore, the distance they travel, which would be big F and big G. So if little f is going slower, doesn't that mean that it has to be behind all the time then if they start the same, but little f is a smaller speed, then it's going to be behind. So big F is going to be less than big G. Its distance traveled is always going to be less. Okay? So that's as a speed limit law. Now let's talk about as an area. So let's say here's A, and here's where they start, and here's little f, and little f's like this. And it said little f is always littler than little g. So that means, right, I should have started right at 0. Right? Well, not little f and little g necessarily. Okay, so they start together, but little f is always less than little g. So now, what's big F? Big F is the area from here to wherever. Here's X right here, right? So big F is this area. Big G is that area. Doesn't big F always have to be less than big G, right? So if the little f graph's always under the big G graph, or little g graph, then the big F and big G, which are the areas, have to be likewise. Okay, so it's kind of the same idea. Same idea as with slope or speed. So it's really just a variation of the speed on the law. Okay, what else? What else? And that's how you could explain it, right? Just a graphs and words. Okay, 5.3, 48. Okay, so what 48's about is it says that the derivative, and here's their notation, the derivative of the integral a to x, little f of t dt, is not equal to the integral from a to x of the derivative dt, little f of t, dt. All right, now, what a bunch of notation. Oh my goodness. Okay, but let's work this through a little bit. Now this side should look familiar. Okay, did I write that down wrong? Isn't this x? This is x right here. I was going to say that to make sense. All right, so this is, we're familiar with this side over here, right? Isn't that fundamental theorem part 1 right there? Okay, that's fundamental theorem part 1 right there. Okay, this side, so what's the difference here? Okay, what's the difference here? Here's the difference. Look, well, let me, in the square brackets right here, what do you got? What is this? What's another name for this in the square brackets? F. Wouldn't this be f prime? This would be the derivative of little f. So this would be like f prime. Okay? So what they're saying is, now, and what does this mean? Fundamental theorem part 1 tells us this means what? Antiderivative. So this is saying do the derivative of the antiderivative. Those should cancel each other out, right? This side is saying what? Do the antiderivative of the derivative. Well, shouldn't those two cancel each other out? And so shouldn't they be equal? Shouldn't this side give us little f, and shouldn't this side give us little f? Well, it's kind of like square root of x squared and square root of x all squared. Those should undo each other. But unfortunately, the order you do that matters. We're doing this in ours advanced math right now. We're doing inverse trig functions. You guys might remember that when you do the sine of the arc sine of something. Actually, it's the other way around. The arc sine, we're having a test on this tomorrow. See how good you guys are. See if you remember this. Shouldn't arc sine and sine cancel each other out? Shouldn't the answer to this be 5 pi 6? Okay, arc sine's only defined in a certain restricted area. Okay? Try it on your calculator. Try the arc sine, so that'd be second sine. Well, no, that's for you guys. It's inside your trig manual. go into your trig menu there and do the arc sine or sine -1 of sine of 5 pi 6. And what's it give you? It gives you pi 6, right? Sine pi 6, 5 pi 6 is over in quadrant 2. Sine of 5 pi 6 is 1/2. The arc sine of 1/2, what the angle whose sine is 1/2 gives you pi 6. It's going to give you quadrants 1 or 4. Arc sine's only defined from negative pi halves to pi halves. Because you're calculating, because there's a lot of places that get where the sine is 1/2. But as a function, arc sine can only give you 1. So it always gives you the one that's either in the first quadrant for positive or the second quadrant for negative. So they should undo each other, but they don't because of some restrictions. Well, that's what's happening here. That's all this is saying. So this is little f of x on this side, because that's what fundamental theorem part 1 tells us. Now, think of it this way. Do the antiderivative of this. It's going to be big F plus some c, right? It's going to be big F plus some c in here. Then what happens when you do the derivative? What's the derivative of big F? Little f. What's the derivative of the c? Goes away. Okay? The c goes away. Now, what about this side? What's the derivative of little f? We just said f prime. Right? What's the antiderivative of f prime? F, but it's going to be f of x, and that's going to be minus f of a. Remember what we just did a minute ago with fundamental theorem part 2? You do the antiderivative of f prime, you're going to get f, and then plug in an x, plug in an a, or you could call it f of x plus c, right? There's going to be a little f plus c. Why? Because of the way we did the order. If you do the derivative first, get f prime, then you do the antiderivative. If you do the antiderivative last, you're going to get a plus c tacked on. If you do the antiderivative first, you get the plus c, but then you do the derivative, the c goes away. That's the difference. That's all that problem's about. Okay, it's about familiarizing yourself with the notation a little bit, but it's also understanding that order. Okay, so, and then it says they're not equal as long as f of a is not 0. If f of a was 0, of course these would be, right? If f of a is 0, then they would be. Okay, but otherwise, if the c is not 0, they're not equal. Okay, so that's notation. Now, you know, on the quizzes, sometimes there's something similar or something that makes you really think about notation a little bit, a few points maybe. But that's, we do want to be able to read this. We do want to be able to see this and think that means antiderivative. So this is saying the derivative of the antiderivative. I think it's important that when we see that, we can read that and make some sense of that. Okay? So, all right, what else? 49, right with it. Okay, this is something we'll talk more about later when we're reviewing for our final. For right now, I don't think it's something you need to worry about on the quiz tomorrow. But the way this one's worded, could we have done this? Possibly. This is the first time we're seeing it. This is another function that doesn't have an antiderivative. That's why I picked this one. Okay, because we couldn't solve this, right? One of the things we've done so far today already is find a formula for this, right? We did it right back here. Okay, we did it right here. Find a formula for this. What did we do? 3 to x. What did we do? We started by doing the antiderivative, 1/3 x cubed. This one, unfortunately, we cannot do that because there is no antiderivative of this. Okay, so we couldn't do that antiderivative and use our free initial condition. We couldn't do it. All right, but it doesn't matter. We don't have to do it. It says, but it says, what do you mean? It says find a formula. No, it says find a formula for the derivative of big F. But then they throw this x squared in here, and that's what complicates it a little bit. All right, but the derivative of big F is going to be what? Little f. This is little f right in here, right? So the derivative of big F is going to be little f. So I actually told you that one of your easiest questions on the quiz would be something like this. So let me change this problem just a little bit, and then this problem becomes the easiest problem on the quiz, right? I could have said find this, or I could have said find this, right? Or I could have put a derivative outside of this. Any one of those three, if I put a little derivative sign outside of this, dx outside of this, or I wrote it like this, or I wrote it like this, the answer to all three of those is what? cube root of 1 plus x squared. You'd be done, right? So if I ask it like that, right, because in here it's got to have t's, when it comes out it's got to have x's, but that big F represents the antiderivative of what's inside, and if I tell you to do the derivative of it, then it gets you what's inside. So that question could be on there for sure. Okay? Now, by putting the x squared in there, that changes just a little bit. Okay? That changes just a little bit. So, forget this for a second. And now let's just look at this. Because I would say to you, we've done this before. So forget that. Just look at this. What does that make you want to write down? What's that make you want to write down? Little f, probably little f, or can I just do f prime? Same thing. What do you do with the inside? Leave it alone. Times derivative of the inside. Right? Something like that, right? If we hadn't been complicating this with all of our new notation and everything, if I'd have given this to you 2 weeks ago, if I'd have said this, I think everybody would have written that. I think you'd have been right, but now you got this other stuff kind of floating around in there, so you're mixing that in there. But this is just a derivative of the outside, big F, inside left alone times derivative of the inside. Okay, now you're right. What's big F prime? That's just little f, right? That's little f with an x squared plugged in times 2x. So how do we do little f with an x squared plugged in? Where's little f? Little f's right here. So this would be cube root of 1 plus what? X to the 4th. Because we got to plug an x squared in. So we got to put an x squared right there. So it's going to be x squared squared. And then times 2x. And then you'd be done. So that problem just by putting that x squared in there, it just added a little more to it. Okay, it added the leave the inside alone and whatever. Okay, where you're going to see that on the final, you'll actually see this problem right here. They'll put the x squared right there. And then they'll say do the derivative of that. Well, what we will talk about later is then we'll just say, well, this is just something out on the inside. They stuck something on the inside. So what you do your normal derivative, which would just be this, stick this in, and then tack on the derivative of that. That's all you do. But I'm not going to give you that, okay, tomorrow. You won't have to do that tomorrow. So you'll just have x's up there, and I would give it to you maybe like that, okay? And if that's the case, if I'm asking for the derivative of big F, that's just that in there. Derivative of big F is just going to be that in there, except with an x in it. Okay, except with an x in it. So that's the only part of that I would make you do tomorrow. All right, what about 19 through 30? Any of those? Because that is a bigger part of the quiz tomorrow, so we definitely want to do some of those.
Number 28.
Yes. Let's look at that. Now, I would never write it with that dx on top like that. I would write it like this. Okay, and put the dx over here, but with fractions, a lot of times they want to stick that up top. And then it goes -2 to 5. All right, so let's talk about antiderivatives. Everybody turn to page 333, if you would. Turn to page 333. Okay, remember when we had that whole big list of derivative rules? Okay, had a whole big list of derivative rules. We're not going to have a great big list of antiderivative rules. Matter of fact, that's it right there, page 333. That's our list of antiderivative rules that we need to know. Okay? Now the trick is going to be making our functions look like one of those so we can do an antiderivative. Okay? So what's the first one? First one's a power rule. We just know that if you got a power, you raise it up 1, divide by the new power. Okay, like we did our 1/3 x cubed. Okay, so we got to know the power rule. What's the next one? Well, the next one's the one we're going to use right here. The antiderivative of 1 over x, x to the -1, is ln x. Well, doesn't that make sense? Doesn't that make sense? Because the derivative of ln x is 1 over x. So the antiderivative of 1 over x is going to be ln x. Okay, now notice they put bars around it. They put bars around the x. And that's because ln, you can only put positives into ln x. So if x is negative, we have to be able to we have to turn it positive. Okay, so therefore, that's something we do have to put in there. We do have to put bars around when we do that one. So we're going to have to remember that. Now, if it shows up tomorrow and you forget the bars, I'm not gonna count them. Okay, on the gateway test over, because we'll have practiced more minute. But that we just gotta know that we just gotta know our basic derivative rules in reverse. Okay, antiderivative of e to the x is e to the x, of course. The other one, the 2 to the x, I'm probably not gonna get into giving you any of those right now, but yeah, we would tack on a 1 over ln a, because when we do the derivative of a to the x, like 2 to the x, we get 2 to the x times ln 2. We do the antiderivative, it's going to have to be the opposite. You're going to have a 1 over ln 2. Antiderivative sign, we already talked about, is negative cosine. Antiderivative cosine is sine. Those are just basic ones. And tangent, remember the derivative is secant squared, so the antiderivative of secant squared would be tangent. That's what we should recognize. And then the two, the arcsine and arctangent. Remember the arcsine had 1 over the square root. Now, again, not going to get into those tomorrow, arcsine, arctangent. Okay, not going to mess with those. So don't worry about them. Okay? Just your basic, maybe a sine or a cosine or a power rule or 1 over x. So what's this going to be? The plus 3 is just a shift, so that doesn't affect anything. So this would be this right here, ln, right bracket, negative 2 to 5. Put in a 5, that'd be ln 8, minus, put in a negative 2, plus 3 is 1, ln 1. Now we should simplify that. What's ln 1? 0. This is ln 8. Now if you type that into your calculator to check, my guess is they gave you 3 ln 2. Why? 8 is 2 cubed, and then there's a rule with logs where you can bring that 3 down. I don't care. I'm perfectly fine with ln 8. But if you check it on your calculator, it probably gives you ln 2. Remember, that's just a number. ln 8 is just a number. It's a fixed piece of area. Okay? So there you go. Turned out the bars didn't matter, right? Bars didn't matter here. All right. But all right, so that's what that one would look like. And again, check. What's the derivative of ln x plus 3? It's 1 over x plus 3 times the derivative inside. What if there had been a 2? Now, probably not going to get that messy, but if there had been a 2 here, we'd have to kick out a 1/2, right? Because on that 2 on the inside. So let's just review that real quick. So we've done this, okay? And we haven't written it with this notation. We've done it this way. So what if f is sine 2x? Okay? What's big F? What's its antiderivative? What's it going to be? Negative cosine. Inside always stays the same. But isn't there going to have to be a 1/2 out there? And what if you forgot the negative? Well, you would just check it. So what's the derivative? Well, the 1/2 would stay there. Derivative of cosine is negative sine. You'd say, oops, it looks like I forgot it. The 2x stays alone. Oh, but then you got to kick out a 2. Oh, the 2 cancels, and we get negative sign. Oh, I better have a negative there, so that way that cancels. Okay, now it checks, right? You just check. Guess and check. So there's not going to be very many that you have to do an antiderivative on tomorrow, but a few just like this page right here. Okay? All right? All right, any others in 19 through 30? 27. Okay, so integral from 1 to 4, 5x plus x to the 3/2 dx. So this is power rule. We don't worry about the parentheses, don't really matter. So we're going to raise this up to a 2 and divide by 2. So 5/2 x squared. Plus, we're going to raise that up to 5/2. So that's going to be x to the 5/2. And then we're going to divide by 5/2, right? Well, dividing by 5/2 is the same as timesing by 2/5, right? So we're going to raise it up 1, which is 5/2, and then divide by 5/2, which is times 2x. Now, again, check it. So bring the 2 down, it cancels that 2, you get 5x. Bring the 5/2 down, it cancels the 2/5, you drop 1, x to the 3/2. Okay, and then we put in a 1 and a 4. Now remember, tomorrow's going to be no calculator, but these all work out pretty nice. So 4 squared is 16, so 5/2 times 16, the 2 cancels 16 is 8, 8 times 5 is 40. Okay, plus put a 4 in here. Do this first. The bottom number means what? Square root. So put a 4 in here. The square root of 4 is 2. 2 to the 5th is 32. We get 2/5 times 32. That's not a lot of fun, but that's 64/5. Okay? Minus, now we put a 1 in. Okay, here's where the parentheses become important. Okay, now we put a 1 in. That'd be 5/2. Plus, we put a 1 in here. 1 to anything is 1, 2/5. So yeah, you'd have a little bit of fraction thing to do here. Okay, so maybe on this one, you'd say 5 goes into 60. That'd be 12 times 12 and 4/5. That'd be 52 and 4/5. Some people like to keep them as improper and do that. This would be a common denominator of 10. So this would be 25/10. And this would be what would that be, 4/10. That's 29/10. What's that, 2 and 9/10? Okay, so now you got 52 and 4/5 minus 2 and 9/10. Well, that's 52 and 8/10, and so you do the rest of it. Just arithmetic. I don't know. I'm probably not going to get too much into fractions, but there will be some. There will probably be a little bit of fractions on a few, maybe, that you have to do. Okay, and you can get a common denominator. Okay, but yes, when you get into these power rules, James, that's a good question. When you get into these power rules, it can get into that, right? It can get into that a little bit, especially. But usually we're going to make them work out nice, at least with the square root part of it and all that. Okay, that part's going to work out okay. All right, I had a couple others that I worked out here just to walk through them real quick. So remember, square root of x, that's x to the 1/2. So you raise that up, that'd be 3/2 divided by 3/2 would be 2/3. 2/3 x to the 3/2. Put in a 4, square root of 4 is 2. Cubed is 8. 8 times that, 16/3. Put in a 0, of course it's just 0, so that works out a little nicer. 16/3. That'd be this area right here. Square root of x, 0 to 4. Okay? Sine x. Of course, we knew that'd be 1 because we already talked about one hump was 2. We talked about a hump of the sine curve was 2, but now we work it out. Negative cosine pi halves to pi, plug in a pi. Negative cosine pi, negative cosine pi halves. Cosine pi is -1 already, so that's +1. Plus cosine pi halves, which is 0, so you get +1. Okay, so that's what your work would look like on those. Okay, all right. Okay, what we didn't talk about were the chart kind of questions. Nobody really asked about any of those. I'd be glad to help you when you have some work time here. Our work time's today is mostly just going to be on these things. That's basically the homework that we have. Okay, I do want to talk to you here just quickly about this idea of antiderivative and just show you a couple little trickier ones just for a minute, but then give you some work time on ones. On some of those, but let's just review for the quiz just real quickly. So this, I told you I'd put this thing up here. So finding areas geometrically. Okay, so just here's a definite integral. Find the area from 2 to 5. Shade it in, and be able to do triangles and half circles and so forth. Remember, area of a circle is pi r squared. Okay, so half circle, obviously half pi r squared. Remember splitting up your integrals, right? Splitting them apart. That's where, well, for example here, if I give you, of course, now that we have splitting them apart, it's not as big a deal now that we have the fundamental theorem part 2. So if I had the integral from 3x, let me remind you what we have. Let's do it in such a way that this would really matter. The splitting of integrals. Let's say I told you, because otherwise you're just going to use fundamental theorem part 2, so it doesn't matter. So let's say I told you the integral from 2 to 4 of f was 9. Okay? And I ask you to find the integral from 2 to 4 of f of x plus 3 dx. Is that answer 12? It's not 12. So you got two ways to think about it. You can either split it apart, right? And if you split it apart, this part here is 9. What's this part? It'd be a horizontal line of 3 from 2 to 4. 2 wide, 3 tall, that's 6. Be 9 plus 6, the answer would be 15, right? Or you can think of that as the F graph shifted up 3, which adds how much area? A 3 by 2 strip. Remember that? So you take the F graph, which has an area 9, you shift it up 3, you've now added a 3 by 2 strip underneath it, which is 6. 9 plus 6 is 15, right? So that'd be one where the antiderivative, so if you remember the ones we did in the homework, I gave you like x squared plus 3. And we didn't know how to do x squared yet, but I told you in the directions. The direction said, okay, the integral from x squared to is 9. And then I gave you x squared plus 3. How do you do that? Well, you split it apart or whatever. Okay. Now, if I gave you x squared plus 3, you just do the antiderivative and do fundamental theorem part 2, right? So if I ask it like that, that'd be a way that would make you think about that. Okay, so keep that in mind as far as the splitting up of the integrals. Okay, then we got into the area function is the antiderivative, which brought in all the chart stuff. So once we knew that, once we know that big A or big F or big G is the antiderivative, now we can do all those chart questions. I hope those are easy. And you're going to have some of those, and those should be easy. Remember, the left endpoint doesn't matter. The left F edge gives you the plus C, but as far as chart, it doesn't matter. The local max is going to be the local max. It's going to be when little f goes from positive to negative. Okay? All right? And so those questions, that part of it should be easy. And then we learned the fundamental theorem part 2, which we've been kind of focusing on today, where we have those problems we just did. Antiderivative tends to be minus 7. Do that. Just some basic antiderivatives. Okay? All right. So with that done, so we talked about indefinite intervals. Okay, so let's just write down a few. So we already talked about page 333. So let's just quickly here. We're going to take 5 minutes, 10 minutes tops, because the problems in the book just kind of lead you and help you what to do on the new stuff. But just start with some simple ones. So remember our notation. An indefinite interval. So this just means what? Do the antiderivative. It just means do the antiderivative. It's an indefinite interval. This just means do the antiderivative. So this is going to be what? 1/3 x cubed plus c. Boom. Done. Just like if this was a gateway test, there's your answer, number 1. Right? That's it. What's this? Negative cosine x plus c. Right? This is just saying do the antiderivative. All that symbol means. An integral symbol with no numbers on it just means do the antiderivative. Okay? Do the antiderivative. It's called indefinite. Okay, so then you get one like this. Okay? Now again, this is a little bit beyond what I'll ask you to do tomorrow. I'm not going to give you any indefinite integrals tomorrow. Okay, the only time you have to do antiderivatives tomorrow would be on an area function 1, use your free initial condition, right, or a fundamental theorem part 2. You do the initial condition, plug in a B, plug in an A, right? That's what tomorrow will be. But you have to do antiderivatives, right, to be able to do fundamental theorem part 2. So just quick practice. So if this was our problem, what would we have? We'd raise that up to 5, so this would be 3/5 x to the 5th. Minus, right? So we're looking ahead here a little bit, just enough to give you enough knowledge that you could, enough reminder here that you could do this on a few homework questions. Okay, what about this? That's going to be its own derivative, right? What about that 3? You have to kick out a 1/3, won't you? Because when you do the derivative, you'll have to kick out a 3, so there needs to be a 1/3 setting there to take care of that. Okay, so we've done that. We saw this one on the one Maya asked about. So this is ln x plus 3. We got to put the bars around it, right? Okay. Just got to remember to do that. And then, what's that last one? That's our tangent of x. And then a plus c at the end. Okay? So that's just kind of a little glimpse of all the different ones we just talked about on page 333, right? I mean, so, and then when there's plus and minus signs, you just go along and do the antiderivative of each one. Okay, but we got days and days of practice of that before we get to the gateway test. Okay, so then the question becomes, what about this? What about a function inside of a function? Okay, now, I'm asking you derivative here. What's the derivative of sine of x cubed? Cosine of x cubed times 3x squared, derivative of the inside. Now I'm going to stick that in front. But, right? Isn't that right? That's a derivative of sine x cubed. Change it. So therefore, the integral of 3x squared cosine x cubed dx had better be what? Plus, isn't that right? I mean, if the derivative of sine x cubed is this, so now think about this. When we were doing derivatives, and we did the gateway test, we would start out with a pretty simple, neat-looking function, sine x cubed. And our finished answer would look pretty messy a lot of times, right? Especially if you had to do quotient rule or product rule, right? You could start with a pretty simple, neat little function and end up with a big, messy derivative. Doesn't it make sense if we go backwards? That we will often start with messy-looking functions, and when we do their antiderivative, we'll end up with simple, neat. How many times did you start off with a messy-looking function and the answer actually got simpler looking when you did the derivative? Not very often. Derivative, start simple and neat, end up messy. Integral possibly means going to start messy and end up looking simple and neat. Okay? So, the task for us is, how do we look at something like this and see that we're going to get it back? Well, it might be the chain rule. The key is there was something on the inside. And you say, hey, there's an x cubed sitting on the inside, and I know when I do the derivative, I'll have to kick out a 3x squared, and guess what? There's a 3x squared sitting right there. Isn't that nuts? Okay? So it's going to look like this. So write this down. This is going to be, and they're going to talk about it in the book. And I'm going to say you start on these tonight. Maybe you just focus on the quiz. You don't even do it. I'm going to give you a handful of odd problems, but you can work on them and make it part of tomorrow's one. Okay? I'm not going to say you have to mess with it. It's totally up to you. But here's how you're going to do this. It's called the method of U substitution is what it's called. Okay? Now, it's going to have some quirks to it and some things we're going to have to work out over a couple days. But its basic idea is this. We take what's on the inside and we let that be U. We just call that, we say let U equal 3, or let U equal x cubed. Okay? Now remember, what we're trying to do here is the antiderivative. We're just trying to do the antiderivative because until we get the antiderivative, we can't do f of b minus f of a. We can't do fundamental third part 2. We can't do any of the stuff we want. Okay? Then we're going to do the derivative of that with respect to x. We're going to do u prime, but we're not going to write it u prime. We're going to write it du dx, and you're going to see why in a minute. Okay, what's the derivative of that? What's the derivative of x cubed? 3x squared, right? Now watch this neat little trick right here. We're going to take this dx and we're going to multiply it over to that side. Yes, it's legal to do. We've never seen something like that, but it is legal. Okay? Now we're going to do that every single time. So at some point here, I'm going to quit doing this in between step. And I'm just going to write it like this. Because every single time I'm going to do du over dx, I'm going to do the derivative, and then I'm going to do the dx over there. So instead of writing 2 steps, I'm going to do it with one. Okay, but for right now, we'll do that. Now, we're going to do what the name implies. We're going to do substitute. Okay? So you basketball players, you understand what's going on here. When we do a substitution, right? Somebody goes in, somebody got to come out. In this particular substitution, we're taking out everybody, right? We got to take out everybody. Okay, starters are sucking it up. Okay, we're taking out everybody. So, well, I take it back. We're taking out all the x's. Okay, taking out all the x's. They all got to come out. The 3 can stay, or the cosine can stay, or whatever. But maybe not. But we got to take out all the x's. So instead of cosine x cubed, I'm going to have 1 in its place. Cosine of u. So all the x's got to come out, and equivalent u's are going to go in their place. So the x cubed has to come out, u comes in. Okay? Now, 3x squared and dx are equal to what? 3x squared and dx are equal to du. Oh. So I can take those 2 out and replace them with just that. Now, look, and that's why I wrote this in blue. Have I substituted everything? Have I taken care of everything? I've taken care of everything. There's nothing left, right? This came out and was replaced by this. This came out and replaced by that. The cosine's still there, obviously. Okay, but equivalent things were replaced. Well, now look how much easier this problem is. That's the goal of u substitution, is to take a messy looking problem and turn it into one that looks like page 333. Now, what's the antiderivative of cosine? Sine. Now, I don't have the integral symbol anymore because it's telling me to do the antiderivative. I just did it, so now that goes away. Okay? And now we put the starters back in. So now we take the u out, and what goes back in its place? X cubed. And there it is. And then we can double check, do the derivative. Sure enough, there it is. The whole reason for u substitution, when you have stuff on the inside. Now, the hope is that whatever's on the inside, the derivative of that is setting around out there too, because that's what's going to happen on a derivative. That's what's going to happen. So notice the answer, much simpler than that. Now, we've already kind of done this. Now, we would not need to do u substitution on this problem, right? We know the answer to this is going to be sine 5x with a what out front? A 1/5. We know that. But you know what? I could apply this idea of u substitution. I could say, you know what? Let u equal 5x. What's the derivative? 5. Multiply that dx over there like I did a minute ago. Now let's substitute out. So that is going to get replaced by a cosine u. Right? Cosine 5x will be the same as cosine u. Now I got to get the dx out of there. Now I don't have dx equal to anything. I have 5 dx. What can I do with this 5? I can divide it over. It's perfectly fine to do that. I can divide that 5 over there. So dx is now equivalent to what? 1/5 du. So I'm going to put the 1/5 out here, and I'm going to put the du there. Because we always like to have the du at the far right end. And when we have a constant, we already talked about how we pull it out. And sure enough, what do you got? Antiderivative cosine is sine. Put your u back in, put your 5x back in, and the 1/5 is sitting out there. And so it works even for that. But we've been just kicking out a 1/5 because we know we're supposed to. And I still would suggest you do that. I'm not saying you would do u substitution like that, but you could. You could see how it works. Okay? All right. So homework. I've just got down, this is in the LH packet. This is more of the f of b minus f of a stuff. So this is stuff that you might get on the quiz right here. 3 through 36, multiples of 3. It's just a handful of problems to work on a little bit of that. I don't really have any other homework to review. The other stuff we talked about for the quiz, but the chart, so if you've got any question on that, the chart, the area function, whatever, that's just what we've been doing. Okay, but that's just a little more practice with antiderivatives, fundamental theorem part 2 stuff. Okay. Tomorrow I'm going to assign a few more of these problems with that u substitution idea, but maybe for right now I won't even. Well, I'll put it up there. It's 5.4. You don't have to. I'm going to give you that tomorrow again. Okay. But it's up to you if you want to get a head start out. We only have an hour, so it's pretty much going to take The quiz is gonna take us pretty much the whole time tomorrow. Okay? This is one of those quizzes that I usually limited the time anyway, because we would then talk about this U substitution stuff after. That's why I wanted to talk about it now, real quick, because tomorrow we probably won't have time, so. All right. If you have any questions, any of those chart questions again, or anything we've done the last few days and want to ask, let me know. Chloe. Okay, what was our plan then?
Okay, so we planned Wednesday, Thursday after school, but I just remembered tomorrow is that mental health training day.
I saw that. I thought, are you going to miss another quiz then? Is that what you're saying?
I don't think I'm going to be ready for it tomorrow anyways.
Okay.
So,
but that goes to like, what, 3:40 or something? I saw the thing.
I think they told us like 4 o'clock at the last meeting. I'm not really for sure.
Okay.
That's supposed to be done.
Okay, so I don't know. So we say, so tonight after school for one, or no?
No, that's not going to work.
So,
Maybe Thursday after school and then Tuesday after school. Would that be okay?
okay. Of course, we're adding one more to the list
Yeah.
of things to